So let's take a look at this again here. What do you need to solve this problem? What information do you need to solve this problem? In other words, from chapter 18, what would you dig up? Okay, you would do KSPF. So if we do KSPF, then we need what? We need the KSP, right? Or do we? Actually, here, let me give you just some numbers. KSP is 1.8 times 10 to the minus 10. And the KF is somebody have their book handy? Do we need the KF? KF for what? What are you talking about, KF? It's trying to dissolve in ammonia. So here's the KSP. Is that it? You want to do KSPF? If you do KSPF, then what is the complex we're forming? Silver complexes with what? And so, how do you know what complexes form? Complexes are Lewis acid-base reactions, right? Lewis acid-base reactions are quite a bit different than Bronsted. Bronsted are super easy to predict. You just take the strongest acid plus the strongest base, they're always the same. Proton donor, proton acceptor. Well, but what about Lewis? For example, this, iron 3, well, ammonia. Ammonia, you should recognize that. Ammonia is a Lewis base, right? And so how many ammonias does iron 3 react with? 6? 4? How many? Because copper reacted with how many copper ions? Reacted with 4 ammonias. And so that means iron should react with 4 ammonias? 6 ammonias? How do you know? Well, the chart, and so you just say, I'll just look it up in the chart, right? But the thing is, you don't want to have to look up everything all the time. This one you'd end up memorizing, but sometimes what you want to do is you want to look for patterns in the chart, right? And that is, have you looked at the KF chart? Have you looked at the KSP chart? No. Have you seen the range of KSP values? Have you seen what types of salts are in the KSP chart? Because the KSP and the KF charts are very useful. Do you know why these are useful? Is because if you think about how many insoluble salts there are, thousands, did they put all thousands? Is that a comprehensive list of salts in the KSP chart? Not even close. So what do you think they did? What do you think the editor did? They tried to figure out which one are the most common. And the same thing with the KF. The KF, they want to put the ones that are most common. The complexes are the most common. And so iron 3 and ammonia are very common. But do you see, let's say, what would you say, hexamine complex? Is that what people said? So do you see the hexamine complex of iron in the KF chart? No, it's not there, which tells you what? It's not common, so we ignore that. And so you look at the silver. What does silver complex with? Silver complex with ammonia, cyanide, thiosulfate, you know, those types of things you'll see in the chart. And which one looks most favorable? Cyanide. You know, cyanide has a huge KF. And so if we use cyanide to complex, it'd probably be much better. The problem with cyanide is it's so toxic. We aren't going to do it. And so what we need to know is we might need to know something like this, that silver complexes with 2 ammonia. How could you have predicted complexes with 2, not 4, not 6? Well, we looked it up in the chart, right? You look for patterns. Well, you know, silver complexes with 2 ions, 2 monodentate ions. Look for patterns. And that's as far as we're going to take it because we don't know the theory well enough just yet. I mean, at this point in Chem 1, B, we aren't digging deep enough into this. And so anyway, we get the KF value. What is the KF value for the diamine silver ion? Does somebody have their...
1.6 times 10 to the 7th power.
Okay, 1.6 times 10 to the 7th power. All right, that sounds good for a start. And so why don't you go ahead and continue working on this and see where you get. Pretend this were a test question and see, would you be... I'll be back.
I mean, that's what people are the most happy to hear. In college, it's Thursday now. figure out what's on me.
I had Friday classes twice. But it was like, one was because it was a Chem, and the other was just, it was Tuesday, Thursday, Friday. So Friday was those labs. 8 to 12. No, but the thing is, like, you get over with Friday, and then the rest of the day is break, do whatever. So, they started. Yeah. But like now that I'm taking night classes, it's like, no, I really wish I could take morning classes. Yeah, I like finishing by the hour. That's how it was like Christmas. I finish by 10:30 every day.
So you don't want to wait?
Yeah.
That one that you said was what would it be?
But then now that it's like 3-hour classes.
Yeah.
Like, yeah.
Just like general.
Yeah.
Well, they open their stuff, right?
Wait, you must people like take it down and then they go.
You do.
That's what I did. Yeah, that's why.
Oh, yeah. Oh my God.
Like 18 and you're in Chem will be on like going to be 21 and also in Chem. I'm glad to be 21 now. When am I going up from school? It's on Wednesday.
What day?
The 25th. March.
I was thinking if you're already putting one, right? Like if you're putting one like this Wednesday or like if you had one day, then you can go on this right.
Yeah.
Party.
Well, yours is supposed to be right now, please. On a Wednesday. Once you're over 18, you're like officially adults. Well, yeah, that's still something. Like, I don't have a party. I've never had a party, but. I always had cake when I was little, but. Now I've outgrown cake now, so.
You're upsetting me.
Are you guys like that?
What? Cake?
Yeah. It's like I like the band cake. You guys have band cake. I'm sure you guys.
Well, he hasn't said anything about it yet.
That's why you always have a song stuck in your head.
Yeah, exactly. I know why.
Oh yeah, you would. Why?
You're upsetting me.
Yeah, exactly. No, I remember actually was like just doing this and then she's like
You want to look at mine? I'll have to do it. Alright, so what's that?
No, it's just, when we did the combined equation, we did it before.
What did your class say when you were
Oh, yeah.
Take them out? Giving stand up.
All right, did somebody get it?
Something.
I tried to get combined equation.
Combined?
I got as far as the combined equation.
Combined equation. You still need more time to work on it? Or I'll give you more time. Why don't you work on it at home, and then we'll. The point of bringing this problem up is, where do you start? You know, in this chapter especially, I get a lot of blank pages because don't know where to start. And so on the test, you know, a lot of people will start with KSP and then calculate the solubility, but you know, that's for water. Silver chloride is not very soluble in water, so the solubility is going to be very low. And some people start with a KF, some people will start with a combined. You know, and so if you do, what you got to do is you got to work through these and then go down all the, you know, the wrong paths. I can sit up here and I can show you, oh, you just do this, this, and this, right? But on the test, you're not going to have anybody showing you what to do, so you got to figure it out. And if you go down the wrong path, you got to back up and try a different route. And so, you know, give this a shot, because in this chapter especially, it's the most difficult because there's so many different ways of starting a problem, and they aren't always right. Whereas in the last chapter, all the problems, in fact, all the titration problems, you know, in the morning somebody asked me, you know, oh, well, what do I use in this part of the titration curve? Well, you can always use the same thing in all parts of the titration curve. You know, it's always the same method. Step A, solution dilution. Step B, strongest acid plus strongest base. You know? You could do every single point in the titration curve using one problem-solving method. You know, doing all the shortcuts, you know, the Henderson-Hausbach, all that stuff was just to do it quickly. But, you know, if you have the time, you don't need to do any shortcuts. You just do every single problem the exact same way. In Chapter 18, there are many different ways, you know, that you could tackle a problem. Not all of them are right. And so in Chapter 18, you got to explore around a little bit and see. You know? The best thing to do is like a chart. You know, the chart is a lot of data. You got a lot of data. You just say, I don't want to look at that chart because there's too much stuff, right? And you say, I use the chart when I need it. When I need the value, I'll just look it up in the chart, right? But and that's the first part. You know, you got a chart like that, but in science, what we do is we do something called data reduction. So we take a lot of data and then try to reduce it down into more simpler stuff, like simpler patterns, and that kind of thing, right? And so in this particular chapter, you know, there's not one problem-solving method. There are a whole bunch. And so what you do is you try to look at all the different ways that they use to solve the problems. You know, the solution guide helps. Solution guide sometimes is wrong. You know, and you'll know it's obviously wrong because when you double check, you know, to make sure the K's match, they don't match. Or when you look at this, you know, stoichiometry, it doesn't match. Like a half a mole of chloride suddenly disappears. You know, where did it go? And so that's obviously wrong. I think you'll see it. But you do that, and then you try to reduce it, you know, into certain strategies for problem solving. And this is like, you know, it's not just looking at, you know, one tree. We're always going to solve it this way, this way, this way. But looking at, you know, trying to look at the whole forest and then reduce it, you know, into something more manageable. Okay. And so, yes, this is going to be a challenging problem to do, but I think it's good because you'll try a lot of different ways and see what happens. All right, so that's pretty much chapter 18, just changing the solubility using different things, methods. But the next two chapters we're covering are related. In chapter 14, it's kinetics. In chapter 15, it's thermodynamics. No, not 15, sorry, 18, 19. Chapter 19 is thermodynamics. I'd like to cover them together because they're related. Thermodynamics and kinetics are related. And so we'll talk about them both. They're related, but you know, they aren't the same thing because kinetics deals with the speed of the reaction. Thermodynamics deals with the driving force of the reaction. And so, you know, one way of dissolving the silver chloride is by using hot concentrated nitric acid. Using thermodynamics, we can figure out how hot does it need to be, and what is the minimum concentration of nitric acid required to do it, you know? Something like that, so we don't have to dump in a whole bunch of excessive, or use excessive temperatures, or dump in excessive amounts of nitric acid, because using high temperatures costs money because you got to heat it. Using excessive nitric acid wastes it, right? And so thermodynamics is very powerful because we can be a lot more precise in what is required to drive a particular reaction forward. And now, if the driving force is big, you know, then usually the reactions happen fast or faster. You know, if you have a huge driving force, you got to worry about explosions. Explosions are just high-speed reactions, you know, out of control. And so we'll be looking at these two topics next, and we'll come back to some of the others. And so when we're looking at the speed of the reaction, let's say we have a reaction where the reactants goes to product. Reactants go to product. And so we'll have something called the rate of reaction. The rate of reaction is, you know, how fast are the reactants consumed. We can measure how fast the reactants are consumed by looking at the changes in concentration. The reactant concentration changes over a time period, time interval. And so delta reactant is just the concentration of the reactants, final, minus the concentration of the reactants, initial. So this is a change. This is going to be a negative because, you know, initially we're going to start off with more reactant, we're going to consume it, and so at the end we're going to have less reactant. T final minus T initial, this will be positive because we'll start off at a smaller time and go to a higher time here. And what we're going to do is we're going to just take the absolute value of this. The reason we're going to take the absolute value of this is because rates are positive. And so we don't want a negative rate. We're just going to say all the rates are going to be positive, so we're going to lose this amount of this. Okay, that's the rate of reaction in terms of the product, reactant, but we can also do the rate of reaction in terms of product. That is delta, the change in the product concentration over a time interval, delta T. This will just be the final product concentration minus the initial product concentration over T final minus T initial. And so what we get from this turns out to be positive because we're going to end up with more product than we start with. And so we don't need the absolute value right here. But what happens if we have something like this? Let's say we have 1A goes to 2Bs. Then the rates are going to be different. They have to be different. The rates are different because when we look at it, we're forming twice as many moles of product than a reactant. And so in other words, B is going to form twice as fast as A, or A is going to react half as fast as B. And so when we have complications like this, then maybe we shouldn't call this the rate of reaction here. We're going to change this a little bit, and we're going to call this the rate of reactant consumption. And then over here, we shouldn't call this the rate of reaction necessarily. We should call this rate of product formation. So what we're going to do for generic, in general, we'll have a reaction AA plus BB plus dot 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 goes to GG plus HH plus dot dot dot. We're going to have a general normalized rate of reaction. So the rate of reaction will equal this. It's going to be 1 over little a times delta A over delta T. Do we need the absolute value sign for this? No, we don't. But you know, instead of doing the absolute value sign, what's another way to change it to a positive number? You know, delta A is going to be negative. And so instead of using the absolute value sign, we could put a negative in front of here. So a negative times a negative makes it a positive. And so this is what your book is going to do. They're going to make a negative sign in front to keep the number positive, which is going to equal negative 1 over B times delta concentration of B over delta T, which is going to equal 1 over G times delta G over delta T, etc. And so that way the rates are always positive. You don't have to use a negative sign, you can just use the absolute value sign if you want for this. So these are the generic rates. And then, you know, if you want rate of reaction of A, you know, the rate of reaction of A is equal to negative delta A over delta T, or the absolute value of delta A over delta T. That's it. But how do we relate it to other things? For example, how would I relate it to B, which is equal to, well, in terms of B, which would be delta B over delta T, I would have to figure out the mole ratio between A and B. And so the mole ratio would just be this, B times, let's do it in front, let's do it in front. Either front or behind. It would be A over, not A, little a over little b. And so the mole ratio. And so as an example here, this would be this. If we did this as an example, this last one we just did. Here I'm using B as a reactant. Here I use B as a product. And so if we do A goes to 2B, then the rate of A is equal to minus delta A over delta T, which is going to equal 1/2 the rate of B, delta B over delta T. And so A is consumed at half the rate B is, etc. So this allows us to relate the different rates. Now, what is the rate of reaction? The rate of reaction in this is equal to, the rate of reaction for A, which is going to be half the rate of reaction for B. Next one. All right, there are two types of rates that we have. The two types of rates are the instantaneous rate and the average rate. The instantaneous rate is equal to the rate at an instant of time. Whereas the average rate is equal to the rate over a time interval. What happens is many rates are nonlinear. You know, nonlinear means they start off fast and then they slow down. Or they start off slow and then speed up. And so that's what we mean by nonlinear. In terms of what that would look like, it would look something like this. If we were to plot the concentration of A, which is a reactant, versus time, a nonlinear would be, let's say, we start off with a lot of A, and so it's highly concentrated. When something's highly concentrated, does it tend to react fast or slow? Highly concentrated versus dilute. Something's very dilute. Like say, if I use concentrated HCl versus dilute HCl, which one would be more reactive? The concentrated. You're going to have a lot more collisions, right, in any given instant because it's more concentrated. The more collisions, the faster the rate. And so typically what happens is the decrease is very rapid at first. But as time passes, it becomes more and more dilute, and it tends to slow down, you know, with time. And so the consumption is very fast and then slows down with time. And so when we think about delta A over delta T, delta A over delta T is what we call the slope of this. And we have two types of slopes. We have the instantaneous slope, which would be equivalent to the instantaneous rate. And we have the average slope, which is equal to the average rate. And so if we were to look at the slope, you can see that the slope is changing with time. You know, the slope is very steep here. That means the rate is very high because it's actually negative right here, but we change it to positive. The rate's very high. And then the slope gradually flattens out and goes almost zero here. And so the rate is very slow as it approaches zero, as it's flattening out. And so how do we figure out what the average rate is, or the instantaneous rate, or any of this is? Well, we do it experimentally, you know. We do it experimentally by, to determine the rate, we just plot out the data. So we measure the concentration with time. You know, if we only took two measurements, let's say I took one measurement here and one measurement here, two measurements are not enough, right? Because two measurements, you don't know what the curve looks like. How many points? We only need 2 points to define a line, right? But that's a linear line. It might not be linear. So how many points do we need to define a curve? What's the minimum number of points we need to define a curve? Well, not 2. Because if we use 2, then we don't know that it's straight, you know? We don't know how deep it is here. We need 3 points, and hopefully the 3 points are spread apart. Because if we do 3 points very close to each other, does it look much like a curve? No. And so we need 3 points that are spread apart so that we can see. If the third point is here, then oh yeah, this is a curve. But if the third point is here, is that much of a curve? Did the rate change much? No. It looks pretty linear, you know? And so we need 3 points to define this, but you know, 3 points isn't the best, because if we have more points, we have less error associated. And so we just try to get a lot of points here to define the curve. We get a lot of points to define the curve, and then we look at the slope. Because calculating the slope from points, 2 points, is fairly straightforward. Let's say I pick this point here, and I pick this point, and then I calculate my delta y, and I calculate my delta x, and I get my slope, right? Now that slope is going to be the rate. Will it be the average rate or the instantaneous rate? This is going to be the instantaneous rate or the average. When I calculate the slope, it's going to be the average slope over this time period. The slope is actually changing over this time period because here the slope is a little steeper, here it's not as steep. Do you see how the slope is changing? And so we call this the average rate over this time period. So if we take the rate here and the rate here and divide it by 2, that's the average. And so we can calculate the average rate between any 2 points here. How do we get the instantaneous rate? And so the slope of this, actually the negative slope of this, is equal to the average rate. Over, okay, I have to call this, so what am I going to call this? I'll call this T3 and T4. And so this is the average rate over the time interval T3 to T4. And so this would be, let's say, the concentration of A at time 3. This is the concentration of A at time 4. And so the average rate is just, you know, A at time 4 minus A at time 3 divided by T4 minus T3. Here. And then we'll take the negative of this whole thing. And so this would be the average rate. So that's not difficult, right? Determine the average rate over any time interval here. But let's say I want the instantaneous rate at T3. It's not going to be the same thing, right? And so what is the instantaneous rate at T3? How would I determine the instantaneous rate at T3?
You have to approach it from the left and you have to approach it from the right. I'm just thinking of calc right now.
Oh,
You
approach
have
it.
to approach it from the left
Yeah.
and approach it from the right.
Yeah, that's one way. But how would we do this? You know, and how would we do this on a piece of paper? Well, on a piece of paper, we would eyeball it. You know, it's not going to be perfect. What we do is, at time 3, we'd eyeball and draw well, it's a line. We draw the tangent line. And so here we have the tangent line like this. And so, yeah, off to the left and off to the right, it looks symmetric. You know? That should be good. And so we draw the tangent line, and then we determine the slope of the tangent line. The negative slope of the tangent line is equal to the instantaneous rate at this time interval, T3. And so we could draw the tangent line anywhere to get the instantaneous rate anywhere. And so the situation here is the average rate and the instantaneous rate are continuously changing. In fact, do you see the instantaneous rate just changes all the time through here? So it makes it tough. This is nonlinear. Sometimes rates are linear. When rates are linear, then it's very easy. You know, at least the math is very easy. Here. This is when we have a linear rate. Let's say we're collecting data. We collect 3 data points here, and wow, it looks pretty much on a straight line. We collect more, and then we confirm that. Yes, you know, this is a straight line. And so here, the slope of the line, the negative slope, is going to equal both the average rate and the instantaneous rate, which is just the rate of the reaction. And so in this chapter, you know, what we got to do is we got to take some measurements. We have to take measurements and then we make a plot and then we analyze the plot to get the rate. Now, what will you call the rate over here? The rate is always changing, so it's difficult. If somebody were to ask you what is the rate of the reaction, you'd have to specify something. You'd have to ask them at what time or at what concentration. Because the rate depends on the concentration and at what time it is. Well, what we want to do is we want to look at the pattern, and then what we'd like to do is, you know, if we know the pattern, we'd like to make predictions. And so one of the predictions would be over here, you know, at what time would the concentration of A go to 0? You know, we could sit there and wait. Do we have to collect data until it goes all the way to 0? Like, you know, for example, you know, at how many milliliters should the pH of your titration yesterday take to hit 13? A pH of 13. How many milliliters of sodium hydroxide would that take? A lot, an infinite amount, right? So are you going to wait until the pH goes to 13? No. The same thing here, you know, especially if this is a slow reaction, are you going to stick around and wait until it's 0? No, what you're going to do is you're going to collect some data up here and then just calculate how long it would take, right? You aren't actually going to wait around and do that. You just make sure it's linear and then we can calculate, right? Here it's easy because calculating this, a straight line is defined by mathematically by this equation, y equals mx plus B. Y here is the concentration of A. M is the slope. X is T. And B is A initial. This is A at time T. So we just set this to 0 and then figure out what the time is. Right? Do a calculation easily. All right, so doing calculations here, it's easy to predict. The rate doesn't change. Everything's the same. But over here, you know, how long is this going to take to hit 0? Forever, right? And so we aren't going to be collecting data forever. What we're going to do is we're going to collect a certain amount of data, and then we're going to use some calculations to predict. You know, we can predict how long it takes to get here, let's say here, to this concentration. How long it takes to get here. Or we could say, you know, after 10 years, what's the concentration going to be? How much of it do I have left over? You know, we aren't going to obviously wait around 10 years to find out. We'll just do a calculation and find out. And so how do I mathematically define this? You know, the equation of this is y equals mx plus b. What is the equation of this? And so this chapter focuses on this. This chapter focuses on a lot of kinetics is nonlinear. Therefore, we need to define this curve mathematically. How do we do that? The answer is, how do we do it? With math. With what kind of math? Calculus. Is calculus a prereq for this class? No, calculus is not a prereq for this class, so we aren't going to be using calculus. We're just going to use the results from calculus. And so, and then we're not going to be doing all scenarios. We're just going to be doing a limited number of scenarios, you know, to keep the math simple. So, for example, we won't be doing like a, you know, multi-variable calculus required for this? And so we're going to be doing single variable, limited. And if we do single variable, we're only going to be looking at 2 scenarios for nonlinear. Keep it very simple. And if it doesn't fall within those 2, or we can't make it fall within those 2 by making some assumptions or doing some changes to how we run the experiment, then we aren't going to cover it. And that's going to be beyond the scope of Chem 1B. And so what are the 2 common patterns that we're going to see here that you should be able to recognize? The 2 common patterns that we're going to see nonlinear, sorry, linear is easy, 2 nonlinear patterns you should recognize. I'm going out of order from the chapter. We're going to come back to rate laws in a little bit, so I'm jumping here to this because this is what you want to train your mind to see. The first pattern is this. If we start off with a concentration of A and we cut that in half, so we have 1/2 the initial concentration here. This is the initial. So we cut it in half. It takes this much time. The time, we call this T1/2. The amount of time it takes to consume half the initial. And it comes out here, let's say. Okay. Then we start over. Now this is my new initial. With my new initial, I've cut it in half again. And so this would be 1/2 my new initial, or 1/4 the original initial, right? And then how long does it take? Well, if I do 1/2 the new initial, and it takes the same amount of time, T1/2, then we call this a first order decay. This is called first order kinetics. And in other words, each half-life, each successive half-life is the same. And so if I go another T1/2, do you know what it's going to be?
1/8.
Yeah, maybe 1/8 or half. If I go another T1/2, it's going to be 16, etc. And so we get a curve that looks like this. This is first order. If it's first order, then we know the mathematics for this, and we can easily make a prediction. You know, after 10 years, you know, what is the concentration going to be? Or how long would it take to get to maybe 1/1,000,000 of my initial concentration? Stuff like that. All right, the next pattern you got to memorize is this. As we're doing the reaction, and we're measuring the concentration, we see this happening. Oh, actually, I need to say a couple more things about this. This isn't as important, but what happens is the instantaneous rate gets cut in half each time. And so here, I'll start off with this instantaneous rate, and then at the half-life, it's 1/2. The slope is 1/2, my original. At the second half-life here, the slope is 1/4 my initial. And so here, we'll call this the rate, initial. And so this would be 1/2 the initial rate. This would be 1/4 the initial rate, or 1/2 the new rate here, etc. Can you guys read that? These pens down. 1/2, 1/4 the rate. This is the instantaneous rate. The other pattern you need to learn to recognize is second order. With second order, what happens is, if we start off with A initial here and we cut it in half, let's say it takes this long, T1/2, we cut it down here. Then we cut this one in half again. We cut this one in half again, it takes twice as long as the previous half-life. So this would be 2 times the original T1/2. And then we cut it in half again, and okay, so T1/2 initial, this would be, the time interval from here would be 2 times T1/2 initial. And so each successive half-life doubles the amount of time. So actually I should just do this. I'll just call this T, and then from here, this would be 2T, or altogether, from the beginning, it would be, if this were a T, and then from here to here is 2T, then from the beginning, it's going to be 3T. And then here, from here to here, it's going to be 4T, which means from the beginning, it's going to be altogether, 7T. Does that make sense? Doing it like this? In other words, each successive half-life doubles from the previous one. And so the curve looks a little different. And so how can you recognize this pattern? Well, one way to recognize the pattern is to see, you look at how it decays and you see, cut it in half, did it take this much time, and cut it in half again, how long did it take? Do that. But doing that requires you to collect a lot of data because you need to see the full structure of the curve, right? And to collect a lot of data, if the reaction is slow, takes a lot of time, right? And so could we figure it out just by taking 3 data points right at the beginning? Here, here, and here? Is that enough data to figure out? If I took 3 right at the beginning, could you figure it out? Well, it depends on how much experimental error there is. If it's perfect, the data has no error, then yes, you could figure it out because the curve is going to be slightly different for both scenarios, right? But if there's a lot of experimental error, then it's very difficult. But technically, yes, you could figure out what it is without seeing the full curve if you know the math. And so this is what we're going to do. We're going to focus on these and then look at the mathematical equations defining these and look at the restrictions that we're going to place on these next time. Okay, but just get familiar. Linear is called 0 order. And so we have 3 common scenarios. 0 order, which is linear, first order, and second order.